क्योंकि तुम ही हो, अब तुम ही हो, जिंदगी अब तुम ही हो, चैन भी, मेरा दर्द भी, मेरी आशिकी अब तुम ही हो. Well, on that Indian note, welcome to the 13th episode of the Divine Intervention Podcasts. My name is Divine. I am a fourth year medical student. Some friends of mine, I have an appreciation for Indian music and I've been trying to learn one song. So I was discussing with some friends of mine yesterday about trying to learn this specific song. That was just a teaser release for my new album. I'm just kidding. But hopefully I can learn that song at some point in the future. Okay, so today we're going to be talking about metabolism. I'm going to break this up in parts. Metabolism is something that's probably a little too big to discuss in one podcast. So I'll discuss it over a series of podcasts. And by the end, hopefully you should have a very good review going into step one. So let's go ahead and jump right in. So the big things I'm going to talk about today, I'll talk about nucleotide synthesis, and I will also talk about some problems with proteins and drawing a lot of like pharmacology and other biochemistry and pathology and all that crap. So let's go ahead and start. So summary of nucleotide synthesis. Remember that nucleotides, right, include DNA and RNA, right? So to make DNA and RNA, you do in fact need nucleotides. And nucleotides basically contain a sugar, a nitrogen base, and a phosphate group. Okay, a sugar, nitrogen base, and a phosphate group. So that nucleotide, the precursor to a nucleotide is a nucleoside. A nucleoside is just the sugar and the nitrogen base. You haven't added a phosphate group just yet. Okay, but those nucleosides need to come from a nitrogen base. Okay, and those nitrogen bases can be one of two kinds. It can be a purine or it can be a pyrimidine. Okay, so you start with the nitrogen base. If you add a sugar, you form a nucleoside. If you form a phosphate, you form a nucleotide. Okay, and those nitrogen bases, like I said, they can be one of two kinds. They can be a two-ringed nitrogen base. They are called the purine nitrogen bases. Those include adenine and guanine. Okay, and the way you differentiate between adenine and guanine is adenine has an amino group at like the topmost position, like the 12 o'clock position. Guanine has a ketone, right? So it has like a carbonyl group, carbon double bonded to an oxygen. The pyrimidine nitrogen bases, they're one ring nitrogen bases. Okay, and there's three kinds. There is cytosine, there's uracil, and there's thymine. There's a classic mnemonic called the PI that can help you remember those three. And one nice thing about them that I think is actually kind of helpful is that order also shows you how those nitrogen bases are made, right? So cytosine, if you deaminate cytosine with cytosine deaminase, you make uracil. You'll see a pharmacology time with that in a bit. And if you methylate uracil, you actually form thymine. Okay, so you'll see a pharmacology time with the first step shortly. And this sugar that joins up with a nitrogen base to form a nucleoside, where does this sugar come from? The thing is, the sugar actually comes from the hexose monophosphate shunt, which is also known as the penthose phosphate pathway. So that pathway makes ribose 5-phosphate. That ribose 5-phosphate can join up with a pyrophosphate group from ATP, right? So two phosphates to make something called phosphoribosyl pyrophosphate. And the enzyme that makes that happen is PRPP synthetase. Okay, so that's a summary of nucleotide synthesis. So now we know how to actually synthesize nucleotides. Let's then go into a little bit more detail. But first, let's talk about pyrimidines. As you can see on the second slide, I say that pyrimidines, to make them, you make the nitrogen base first, and then you add the sugar. But for the purines, you make the sugar first, and then you add the nitrogenous base. So let's talk about pyrimidines. Let's make the nitrogen base first, and then we add the sugar. So to make the base first, all of this actually happens in the cytosol, or nucleotide synthesis in general happens in the cytosol. So the first thing that happens is that you condense glutamine and carbon dioxide with some other stuff, okay, and you make something called carbamoyl phosphate, and the enzyme that makes this happen is CPS2, carbamoyl phosphate synthetase 2. Okay, and again, this is a cytosolic enzyme. If there's a CPS2, you should probably know that there's a CPS1. Okay, remember the 1 in CPS1 as being like an I to help you remember that CPS1 works in the mitochondria. Okay, works in the mitochondria of the urea cycle. We'll talk about that in a later slide. Okay, so you make carbamoyl phosphate, and then that carbamoyl phosphate is then made into orotic acid by some magic that are not really interested in for the purposes of board exams. And then that orotic acid is the nitrogen base. So we've accomplished our first objective. Okay, now we want to make a nucleotide. Okay, so we are adding a sugar and we are adding phosphate, right? And that's done by an enzyme known as UMP synthase. UMP synthase takes that phosphoribosyl pyrophosphate I talked about on the previous slide, okay, and helps us make uridine monophosphate. I'll talk about pathology associated with that in a bit. And then that UMP is made into UDP. Don't care much about that, but that UDP is a ribonucleotide. Okay, UDP is a ribonucleotide. The thing is, we have RNA and DNA. If you want to go down the DNA pathway, you need to convert your ribonucleotides to a deoxyribonucleotide. Ribonucleotides in general have hydroxy groups at the 2' and the 3' carbons of the sugar structure. Okay, but a deoxyribonucleotide does not have that 2' hydroxy group. It only has that 3' hydroxy group that it uses to form those phosphodiester bonds with the 5' phosphate. So to remove that 2' hydroxy group, we need an enzyme known as ribonucleotide reductase. I'll talk about some pathologies related to that. So that DUDP, you can clip off a phosphate, make DUMP, and then that DUMP can then be converted to DTMP. And if you remember, I said that the difference between uracil and thymine is a methyl group, okay? So this reaction clearly needs a methyl donor, okay? And one high-yield methyl donor that exists in the body is the methylated form of tetrahydrofolate. The methylated form of tetrahydrofolate can give a methyl group to DUMP, and then we make deoxythymidine monophosphate from that. And then that cycle needs to keep going, and I'll talk about some pathologies relating to that shortly. So, what are those pathologies? If you go to the very top of the slide, top right, I guess, I talk about how having a UMP synthase deficiency is associated with orotic aciduria. The thing is, if you have a deficiency of the enzyme that metabolizes orotic acid, obviously your levels of orotic acid in the serum will go up. You'll see how this is related to another disorder that I'll talk about in a later slide. Okay, now ribonucleotide reductase is helps you go from RNA land to DNA land. The thing is, you can actually inhibit that enzyme with an anti-cancer drug known as hydroxyurea. Hydroxyurea, yes, it's an anti-cancer drug, and it is in fact used for some hematologic malignancies. But the thing is, hydroxyurea is primarily used in the real world for the treatment of sickle cell disease, okay, because by some unknown mechanism, it increases the synthesis of hemoglobin F, which is alpha 2 gamma 2. Now, if you then jump down to thymidylate synthase, which helps us go from DUMP to DTMP, that enzyme can be inhibited by a drug known as 5-fluorouracil. Okay, 5-fluorouracil. So 5-fluorouracil is an anti-cancer drug. The thing is, if you look further upstream, there is an arrow going from 5-FC to 5-FU. The 5-FC actually stands for 5-flucytosine. If you remember, this is an antifungal that is used to treat cryptococcal neoformans meningitis in AIDS patients. Okay, the way 5-flucytosine actually works is that it is deaminated by cytosine deaminase. So remember that principle I talked about on the preceding slide. Cytosine deaminase converts the 5-flucytosine to 5-fluorouracil. That 5-fluorouracil inhibits thymidylate synthase. You make less thymidine monophosphate, and then you basically treat the cryptococcal meningitis. Okay, so that's a very nice tie-in there. Now, I also said that for thymidylate synthase to work, okay, you need a methyl group, okay, coming from methylene tetrahydrofolate. So when methylene tetrahydrofolate gives that methyl group to thymidylate synthase to make DTMP, okay, dihydrofolate is made as a byproduct of that reaction. If you want to keep thymidylate synthase doing its job, Okay, that dihydrofolate has to be reconverted back to tetrahydrofolate by an enzyme known as dihydrofolate reductase. Okay, this enzyme is inhibited by methotrexate, trimethoprim, and pyrimethamine. Methotrexate, remember, it causes pulmonary fibrosis as a side effect, and it can also cause a liver dysfunction. And remember that methotrexate can be used to treat hydatidiform moles, right? So like molar pregnancies. Remember the snowstorm appearance on ultrasound of the pelvis. Trimethoprim, it's usually combined with SMX, right? So trimethoprim sulfamethoxazole to treat the pneumocystis jirovecii pneumonia. You can also use it to prophylax against the PCP when the CD4 count drops below 200. And remember that trimethoprim TMP SMX Bactrim, right, can also be used to treat UTIs. It can also be used to treat nocardia. Okay, remember, as a review from previous podcasts, remember that nocardia is an aerobic organism. It's a gram-positive branching filamentous rod, and it's also weakly acid-fast, right? So it stains positive with a Ziehl-Neelsen stain. And then pyrimethamine combined with sulfadiazine can actually be used to treat the toxoplasmosis, right? So classically, if you think about an AIDS patient that has ring-enhancing lesions on an magnetic resonance imaging, you think about toxoplasmosis. Okay, so that's all I'm going to say about this slide. So let's jump on to the next one. So an interesting comparison of two cycles, right? So these two cycles, they are not just intellectually it's stimulating to compare these two cycles, but these two cycles actually like USMLE relevant. Okay, so these two cycles include the Urea cycle and the synthesis of pyrimidines. I just said that to make pyrimidines, you do that in the cytosol. But the thing is, the Urea cycle actually operates in two spots in the body. In a cell. Okay, the first two steps actually work in the mitochondria, and then the final steps work in the cytosol. Okay, you may ask yourself, Divine, this is too low yield to know. Well, think again. It's actually high yield to know these double localization details for step one. So, in the Urea cycle, stuff, including ammonia, is acted on by carbamoyl phosphate synthase 1 to make carbamoyl phosphate. Okay, that's the first step of that cycle. And then that carbamoyl phosphate can be converted to citrulline by an enzyme known as ornithine transcarbamylase. Okay, so ornithine transcarbamylase converts carbamoyl phosphate to citrulline. Okay, and that citrulline can then go into the cytosol to complete the remaining steps of the Urea cycle, right? So it condenses with aspartate and all that fun stuff. Now, so that is the Urea cycle, okay? But the thing is, if you contrast that with pyrimidine synthesis, I said that instead of using CPS1, you actually use CPS2, okay? CPS2, carbamoyl phosphate synthase 2, works in the cytosol, okay? It converts glutamine and CO2 with some other stuff to carbamoyl phosphate, and then that carbamoyl phosphate by some magic becomes orotic acid, and then that orotic acid, okay, is converted to uridine monophosphate by an enzyme known as uridine monophosphate synthase or UMP synthase. Okay, so if you notice, I put two red star X's in those two pathways, right? So first we've contrasted those pathways by location, right? So like mitochondria for the first two steps of the Urea cycle, cytosol for all the steps of pyrimidine synthesis. But the thing is, you can have two enzyme deficiencies in both pathways that can create an orotic acidemia, if you may. Okay, that orotic acidemia, right, it's like similar phenotype, but they're different. There are some extra findings that can tell you that, oh, it's this enzyme deficiency that's in operation versus this other enzyme deficiency, right? So if you have an OTC deficiency, an ornithine transcarbamylase deficiency, you will have a very big buildup of carbamoyl phosphate, okay? And if you're thinking with regards to Le Chatelier's principle from college chemistry, as carbamoyl phosphate builds up, okay, it can spill into the cytosol. Okay, it can spill into the cytosol. That's one fate. Another thing that can happen is, as carbamoyl phosphate builds up, the upstream contributor to the synthesis of carbamoyl phosphate in the mitochondria also builds up. Okay, so ammonia in this case. So you can get a hyperammonemia with OTC deficiency. But this carbamoyl phosphate that spills in from the mitochondria into the cytosol, it can actually just basically join into the pyrimidine synthesis game. Okay, that carbamoyl phosphate, it can be converted to orotic acid, and you can get an orotic acidemia under those circumstances. Okay, Now, if we go to the pyrimidine synthesis side of things, okay, if we have a UMP synthase deficiency, we have a disease known as orotic aciduria. Okay, so if you have a deficiency of UMP synthase, orotic acid builds up. Okay, but because this is part of the pyrimidine synthesis pathway and not the urea cycle, okay, you don't have any elevations in your ammonia. So that is how you tell the urea cycle deficit, ornithine transcarbamylase deficiency, apart from the pyrimidine synthesis deficit, okay, UMP synthase deficiency. And then in the middle, I put as an aside, if they wanted to make this a more nifty step 1 question, they could talk about, a person has hyperammonemia, so right, they have like the encephalopathy you get with too much ammonia dancing around in your blood. But these people have no orotic aciduria. Okay, you may be like, how did that happen, right? So that's one very nice way they can test your knowledge of the urea cycle. Okay, if you have a CPS1 deficiency, your ammonia will build up, but because carbamoyl phosphate is downstream of that, you have decreased levels or normal levels of carbamoyl phosphate. Okay, so that's how you can compare these 3 enzyme deficiencies. In fact, I try to do that on the next slide. If you have a CPS deficiency, it's a urea cycle problem, so your ammonia levels are up, but your carbamoyl phosphate and orotic acid levels are down. Okay, if you have another urea cycle deficiency that's a little more downstream, okay, ornithine transcarbamylase deficiency, your ammonia levels go up. Okay, because again, it's a urea cycle problem. Your carbamoyl phosphate levels also go up because ornithine transcarbamylase converts carbamoyl phosphate to citrulline. Okay, and then your uric acid levels also go up because that carbamoyl phosphate spills into the circulation. Spills into the cytosol, and that joins in pyrimidine synthesis, so you make more uric acid. Okay, but contrast that with the pyrimidine synthesis deficit, like UMP synthase deficiency, where your levels of ammonia are normal, okay, because it's not a urea cycle problem, but your carbamoyl phosphate and your uric acid levels are elevated because, again, these two things come upstream of UMP synthase. And really, the way you treat UMP synthase deficiency is just to give back what is deficient. You give back uridine in the diet, and you can largely relieve the sequelae of UMP synthase deficiency. But if you have a CPS1 or OTC deficiency, it's really bad because that ammonia can build up in the brain and cause a lot of problems for the infant. Okay, so those kids usually don't live super long, unfortunately. So next slide, right? So we've talked about pyrimidines. Now let's talk about purines, okay? So let's talk about how you make purines, and let's talk about how you break purines, okay? So to make purines, right, we said that you start with the sugar first, and then you add the nitrogenous base. Okay, so we make the sugar first. I've talked about how the sugar is made with PRPP synthetase in a previous slide. Okay, so you make PRPP, and then you make something known as 5-phosphoribosylamine with an enzyme known as PRPP amidotransferase. The reason I'm mentioning PRPP amidotransferase is that it's actually the rate-limiting enzyme of purine synthesis. So you definitely want to know that for step 1. So you make 5-phosphoribosylamine, and then you have some magic happen, and then you make inosine monophosphate. Okay, now the inosine monophosphate can either be converted to adenosine monophosphate or guanosine monophosphate, and the enzyme that helps you go from inosine monophosphate to adenosine monophosphate is inosine monophosphate dehydrogenase. Now, why do I mention this enzyme? I mention this enzyme because it's inhibited by certain drugs. Okay, so one drug that inhibits this enzyme is mycophenolate mofetil. Okay, it's an immunosuppressant. It's used after transplants. Okay, ribavirin, which is used to treat RSV and also like Hep C under certain circumstances, also works by inhibiting inosine monophosphate dehydrogenase. And the rate-limiting enzyme PRPP amidotransferase, if you notice, I put like 5 red thins by PRPP amidotransferase. I put AMP, GMP, IMP to help you remember the regulation of PRPP amidotransferase. Those products of that enzyme go back and feedback inhibit the enzyme. And then allopurinol and 6-methylpurine actually go back and also inhibit PRPP amidotransferase. So you may be like, Divine, how is that relevant to our discussion? You'll see why when we're done talking about purine breakdown. I'll talk about some integration with that. So let's break down our purines, right? So again, remember, nucleotide, nucleoside, nitrogen base. Okay, so the nucleotide AMP, GMP, you pull out a phosphate, you make the nucleoside, you pull out the sugar, you make the nitrogenous base. Okay, the nitrogenous bases, hypoxanthine or guanine. Okay, and then those nitrogenous bases, they can be converted by xanthine oxidase, okay, in 2 sequential steps to uric acid, okay, and then that uric acid is actually poorly soluble, right? So if you have too much uric acid in your blood, you could get gout, or you could get nephrolithiasis from uric acid stones. Remember, uric acid stones are radiolucent, so you don't see them on an x-ray, but you can see them on a CT scan. Okay, and then in birds, the uric acid could actually be converted by an enzyme known as uricase to allantoin. Allantoin is water soluble. Okay, it's much more soluble than uric acid. Okay, so now that we understand this, we can then begin to bring in some integration, and then I'll go back to that PRPP amidotransferase story that I was fleshing out a few minutes ago. So one thing we could do is, if a person has gout, right, or they have tumor lysis syndrome, where they have some kind of hematologic malignancy and the person's white cells or whatever are dying, and they're dumping a lot of purines into the serum and making a lot of uric acid that's clogging up the kidneys and also causing gout. You could try to solubilize that uric acid by giving a pharmacological agent that replicates the activity of uricase. Okay, that's where drugs like pegloticase and rasburicase come in. Okay, pegloticase and rasburicase, they are uricase analogs that help you dissolve uric acid nicely by converting it to something that's a little more water soluble. Now, another thing you could do to prevent tumor lysis syndrome, right, is to say, okay, you know what, let me go ahead and inhibit the enzyme that helps us make uric acid in the first place, xanthine oxidase, right? So that's how drugs like allopurinol and febuxostat work. Okay, they inhibit xanthine oxidase, so you don't make uric acid. Now, the thing is, xanthine oxidase, in addition to helping us make uric acid, it actually has another high yield USMLE role. Okay, one thing it does is that it breaks down 6-methylpurine to inactive metabolites. Okay, so if you think about it, if you give a xanthine oxidase inhibitor like allopurinol or febuxostat, you decrease the breakdown of 6-methylpurine, and that can do one of two things. One is that it could do a bad thing to you, right? It could increase the toxicity of 6-methylpurine. Alternatively, if you're a wise pharmacologist or physician, you can actually give allopurinol with as part of the drug cocktail for a person that's being treated with chemotherapy that includes 6-methylpurine to decrease the dose of 6-methylpurine that you have to administer. Okay, so that's a very nice tie-in there. Now, the thing is, if you want to take this nitrogenous base that you got from breaking down the purine and like remaking, if you wanted to say, okay, you know what, why don't I conserve my purines instead of wasting them in the urine? Why don't I conserve them by converting the nitrogen base back to a nucleotide? You do that in a pathway known as the purine salvage pathway. Okay, and the one big enzyme you need to know for that pathway is HGPRT. Okay, HGPRT stands for hypoxanthine guanine phosphoribosyltransferase. Okay, it's the enzyme that takes hypoxanthine and guanine and adds a sugar and a phosphate back, right? So phosphoribosal, okay, it transfers a sugar and a phosphate back to hypoxanthine and guanine and remakes the nucleotide. Okay, so why is it important to know this enzyme? It's important for certain reasons. One is that you have it's the enzyme that helps us in the purine salvage pathway. The other thing is this is the enzyme that's deficient in Lesch-Nyhan syndrome. Okay, Lesch-Nyhan syndrome, it was actually discovered at my med school by a med student, go figure, and some physician. You can look that up in your free time. So, Lesch-Nyhan syndrome, it's a HGPRT deficiency. And the thing is, if you think about it, if HGPRT is deficient, you've basically killed the pathway that helps us deal with nitrogen bases, okay? Because these nitrogen bases, we can deal with them in one of two ways, at least on this slide. You can deal with them with HGPRT, which is what happens more than 85% of the time, or you can deal with them with xanthine oxidase. Okay, so if the 85 percentile plus pathway is gone, then this other pathway then becomes the 100% pathway. Okay, so make a ton of uric acid. So gout is a classic finding in Lesch-Nyhan syndrome, although you also tend to get self-mutilation and all that stuff in Lesch-Nyhan syndrome. So one treatment for Lesch-Nyhan syndrome is that you can give a xanthine oxidase inhibitor to sort of prevent the gouty sequelae that you get with the disease. Although the self-mutilation and the neurological problems, those are unfortunately not very treatable. Now, the thing is, if you notice, another red I put by HGPRT is azathioprine. So the thing is, azathioprine is an anti-cancer drug that is a precursor to another drug known as 6-methylpurine. Okay, so the way azathioprine works is that it's converted to a purine analog, okay, by the action of HGPRT. HGPRT helps us activate azathioprine, helps us convert it to 6-methylpurine. Okay, 6-methylpurine has purine in the name. That should help you remember that it's a purine analog. Okay, so 6-methylpurine goes and inhibits PRPP amidinotransferase. Okay, and by inhibiting PRPP amidinotransferase, you basically shut down the synthesis of purines. It also so happens that 6-methylpurine can also inhibit HGPRT. Okay, so overall you decrease purine synthesis, and that's how azathioprine / 6-MP work as anti-cancer agents. So that's what I'm going to say on this slide. Okay, and let me just talk about one last offshoot of the purine salvage pathway, right? So again, you start with a nucleotide, you break it down to a nucleoside, and then that nucleoside is broken down to a nitrogenous base. Okay, so AMP is a nucleotide, it's broken down to adenosine. Okay, that's a nucleoside, and then you pull off the sugar with actually you don't pull off a sugar just yet. You deaminate the adenosine to make another nucleoside known as inosine. And the enzyme that makes that happen is adenosine deaminase. Okay? And then you make inosine. Inosine, you then pull off the sugar. Okay? And then you're left with a nitrogenous base hypoxanthine. Okay? So, the thing is, if you notice, I put ADA, adenosine deaminase, between adenosine and inosine. Okay, the thing is, if you have a deficiency of adenosine deaminase, it's an autosomal recessive disease, you have a buildup of adenosine. Okay, and again, if you're walking backwards with the Le Chatelet principle, as your adenosine levels go up, your AMP levels go up. If your AMP levels go up, your deoxy ATP levels go up. Okay, and that your higher levels of ATP, that ATP can combine with methionine, okay, to make SAM, right? We'll talk about SAM in a different podcast. As you'll come to know, SAM is a very good methyl carrier in the body. It works like in the adrenal medulla, for example, to help you convert norepinephrine to epinephrine. But that's a different story for another podcast. So SAM, if you pull off a methyl group from SAM, you can actually make something called S-adenosyl homocysteine. Okay, S-adenosyl homocysteine. The thing is, S-adenosyl homocysteine is actually toxic to B and T lymphoblasts. Okay, so if you kill your B and T lymphoblasts, you do not make B or T cells. So you get something called a severe combined immunodeficiency. Okay, so that's the pathophysiology behind adenosine deaminase deficiency being one cause of autosomal recessive SCID. Now, another thing that could also happen is that AMP that's building up, right? Because it's not being, because of a buildup of adenosine, that AMP that builds up, okay, remember, if you remember your negative feedback, that inhibits PRPP amidinotransferase, which, as we said, is the rate-limiting enzyme of purine synthesis, okay? So you also have decreased purine synthesis under those conditions. That's why you can get into a lot of trouble with adenosine deaminase deficiency. So next slide, right? So protein metabolism. Protein metabolism, basically, for the rest of this podcast, I'm just going to talk about how you deal with proteins. Okay, so let's assume you eat some protein-containing dish like meat or chicken or turkey, whatever. Okay, so you guzzle it down your throat, and as it goes down your esophagus, it gets to the stomach. Okay, the stomach. Remember, there's parietal cells that make acid. okay, through potassium antiporter, okay. Is an antiporter, it's an ATPase, right? So you make a ton of acid. That acid denatures the protein, okay, and then that protein, pepsin in the stomach begins to digest the protein, okay. Remember, pepsin is the active form of pepsinogen. Pepsinogen actually comes from chief cells, okay. Chief cells, another cell type you find in the stomach. To actually go from pepsinogen to pepsin, you actually need the acidity of the stomach to make that happen as well. So that's a nice GI tie in there, okay. Now that protein then makes its way to the small intestine, okay, and the pancreas releases certain enzymes like trypsin, chymotrypsin, carboxypeptidase, whatever. They also help with digesting the protein. Although remember that enterokinase is what kickstarts this process, right? So enterokinase converts trypsinogen to trypsin, and then trypsin can then go and break down the zymogen forms of chymotrypsin and carboxypeptidase to the more active forms, okay. So you break down those proteins to amino acids, okay. Amino acids are like the monomers that build up proteins. But another thing that could happen is instead of breaking the protein down completely to an amino acid, you can break it down to like a dipeptide or a tripeptide, okay. And then the dipeptide or tripeptide or monopeptide, which is an amino acid, they can all go they can be pumped into an enterocyte in the small intestine by sodium glucose linked transporter, okay. Sorry, not sodium glucose, sodium amino acid linked transporter, okay. So remember, sodium is primarily an extracellular ion because of the activity of the sodium potassium ATPase pump. So as that sodium goes down its gradient into the enterocyte, you have the active transport, I guess not pumping, active transport of amino acids, okay, or dipeptides or tripeptides. And if you notice in the slide, I say that O versus glucose. I just want to remind you that you cannot transport disaccharides or trisaccharides across an enterocyte membrane with sodium linked transportation, okay. Contrast that with your amino acids where you could take like a diamino acid, okay, a dipeptide or a tripeptide, and bring it into the enterocyte with a sodium linked transporter, okay. Now if you have a problem, some kind of mutation in those transporters for amino acids, you can have two high yield diseases for step 1, okay. You can have something known as Hartnup disease, or you can have something known as cystinuria, okay. And the thing is, these transporters, they do not just work in the small intestine, they actually also work in the proximal convoluted tubule, okay. They actually work in the kidney as well. In fact, I'll just tell you this as a general principle. Most transporters you'll find in the small intestine are also found in the proximal tubule. Why does that make any sense? The thing is, both parts of the body, okay, are involved in reabsorption, right? So if they are both involved in reabsorption, it should make sense that they have similar transporters. If you even wanted a very nice tying here, if you remember, like the sodium glucose linked transporter, right? So we have SGLT transporters in the kidney, like SGLT2, but in the enterocyte, in the small intestine, we actually have SGLT1, right? So remember your SGLT2 inhibitors like canagliflozin and dapagliflozin that basically help you pee out sugar in your urine. So these are sodium amino acid linked transporters. You find them in the GI tract, in the small intestine, and also in the proximal tubule. In fact, if you also think about both parts of the body being involved in reabsorption, you can see why there's microvilli in the small intestine, and there's also microvilli in the proximal convoluted tubule, okay? So just some nice ties between those two parts of the body. So Hartnup disease is basically a problem with neutral amino acid transporter, okay. And again, this transporter is found in the small intestine and the kidneys, right? So if you have a mutation in this transporter, you do not reabsorb a neutral amino acids either in the gut or in the urinary tract. And if you have that, you won't reabsorb tryptophan. Tryptophan is a high yield neutral amino acid. The thing is, tryptophan can be used to make things like serotonin, right? Serotonin is 5-HT, 5-hydroxy tryptophan. But tryptophan can also be converted to niacin. Okay, so if you have a tryptophan deficiency, you can also get a niacin deficiency, okay, with heart valve disease. A niacin deficiency, remember the 4Ds, okay, so like dermatitis, dementia, diarrhea, okay, and death. Death is the fourth D. Guess that's not very ideal. Okay, so you can get pellagra presentation if you have a heart valve disease. Now, cystinuria is a mutation in another amino acid transporter, but this transporter it's classically known as the COLA transporter because it transports cysteine, ornithine, lysine, and arginine, okay, which are all basic amino acids, okay. So the thing is, again, if you have a mutation in this transporter, and like I said, that this transporter operates in the GI tract and in the urinary tract, cysteine can begin to show up in your urine, okay. And the thing is, the cysteine can pair up with a buddy, another cysteine buddy, and you make a cysteine, and that cysteine can form kidney stones, okay, because it's not very soluble in the urine, okay. So it can form kidney stones. Remember, those cysteine stones are like 16 stones, right? So they're shaped like hexagons, like benzene rings. So that can cause nephrolithiasis, okay. So that can be a presentation of cystinuria, okay. And the thing is, those cysteine stones, you can actually solubilize them under basic conditions, okay. So you can actually give acetazolamide as treatment for cystinuria. It helps you solubilize the cysteine stones. Now, the thing is, we like protein, right? But the thing is, protein actually does some bad things to the body, okay. I mean, it's not necessarily bad if you have a good organ to deal with it, in this case the liver and your kidneys to a limited extent, okay. So the thing is, to deal with a protein problem, we also need to deal with the ammonia that we get from proteins, okay. So to deal with that ammonia, we have something known as the urea cycle. But before I can talk about the urea cycle, let me just give some preamble relating to amino acids. Now, the thing is, amino acids, they have two lives, okay? So one life is as being alpha keto acids. The second life is as being amino acids, okay? Now, the thing is, to basically interconvert between alpha keto acid and amino acid, you either lose an amino group or gain an amino group. If you lose an amino group, you go from an amino acid to an alpha keto acid. If you gain an amino group, you go from an alpha keto acid to an amino acid, okay? So to make those interconversions, you need enzymes known as aminotransferases, okay? Aminotransferases, you could also know them as transaminases, just one and the same name for the same kind of enzyme, okay? And these enzymes, they all use vitamin B6 as a cofactor, okay? Pyridoxal phosphate. Hopefully you remember your B vitamins, right? So vitamin B1, right? That's thiamine, okay? Vitamin B2 is riboflavin. B3 is niacin. There's no B4. B5 is biotin. Okay. B6 is pyridoxal phosphate. Hang on. Vitamin B5. Wait. B1 is thiamine. B2 is riboflavin. B3 is niacin. Vitamin B5. Wow. I'm actually ashamed I forgot this. I actually kind of like biochem. Vitamin B5. What is B5? Pantothenic acid. Oops, sorry. So it's pantothenic acid. B6 is pyridoxal phosphate. B7 is biotin. Okay. B9 is folic acid. B12 is cobalamin, right? So vitamin B12. Okay. So just a quick review there. And we'll talk about what you use those different vitamins for in a later podcast. So back to this. So B6 is a cofactor for the aminotransferases, okay? It also so happens that B6 is a cofactor for ALA synthase, okay, which is the rate-limiting enzyme of heme synthesis. And B6 is also a cofactor for glutamate decarboxylase, which helps us convert glutamate to GABA, okay? So hopefully with these other reactions I mentioned, you can see why a person taking isoniazid can get a sideroblastic anemia, because they can, remember, INH depletes vitamin B6. So by having a B6 deficiency, ALA synthase doesn't work, so you can get a sideroblastic anemia because you're not making heme. Alternatively, if you have a B6 deficiency, you have a buildup of glutamate and a downregulation of GABA synthesis. Okay, remember, glutamate is an excitatory neurotransmitter, so you can get seizures with that. So this alpha keto acid amino acid pairing, there's some that I will say are relatively high yield to know for step 1. That's for example like pyruvate and alanine, or alpha ketoglutarate and glutamate, or oxaloacetate and aspartate. Okay, pyruvate, for example, is the alpha keto acid of alanine. So to deal with our protein problem, we need to also deal with the ammonia that comes as a byproduct of proteins, right? So the thing is, one way we can deal with this ammonia problem is to simply just pair it up with a hydrogen ion, okay? You make ammonium, and then you pee out ammonium in the kidney, okay? This is the primary way the kidney deals with ammonia problems for us, but that's a very minor pathway. It doesn't do much, okay? To really get rid of ammonia, you want to condense it with a carbonyl group and another ammonia, okay, into something known as urea, okay? So you make urea, and then urea can travel in the blood nicely. It doesn't cause any problems, doesn't change the pH of the blood, doesn't need any kind of carrier in the blood. So it moves safely in the blood, and then we just pee it out in the urine, okay? So urea is a great molecule. We actually have to make that urea, and it so happens that that urea is made in the liver, okay? That's why if you have liver problems, you can get a hyperammonemia because your urea cycle doesn't work anymore. Okay, so the urea cycle is a very complex cycle, but to be honest, there's not much you really need to know for step 1. There are just very few things that you sort of need to take away, okay? So the thing is, urea contains 2 amino groups, okay? And those 2 amino groups come from glutamate and aspartate, okay? Glutamate and aspartate. So the glutamate and aspartate take ammonia, because remember, glutamate is an amino acid, aspartate is an amino acid as well. So it should stand to reason that these 2 amino acids were previously alpha keto acids at some point in the distant past, okay? So those alpha keto acid forms of glutamate and aspartate receive ammonia, okay? And they are made into glutamate and aspartate, which then donate the amino groups to the urea cycle to help us make urea, okay? And the thing is, for those, because, I mean, think about it, ammonia is not made only in the liver. Ammonia is made in many different parts of the body. It's made in muscle, it's made in spleen, it's made in many organs, okay? The thing is, the ammonia from those many organs have to find a way to get to the liver to participate in the urea cycle, okay? So the thing is, ammonia itself should probably not be traveling in blood, right? Because it's a basic molecule, it will raise the blood pH and you could like die, okay? So the body puts that ammonia in an amino acid format, and then those amino acids, they travel safely in the blood, get to the liver, and in the liver they dump those amino groups, okay, into oxaloacetate to make aspartate, and into alpha ketoglutarate to make glutamate, and then you're good to go, okay? And those are ammonia carriers in the blood, okay? There's glutamine and there's alanine, okay? And alanine primarily comes from muscle, and again, that should also make sense. The body was actually created in a pretty nice way, okay? Because the thing is that alanine is the amino acid that comes from the alpha keto acid pyruvate, okay? And if skeletal muscle is running low on glucose, okay, one thing it can do is to say, okay, you know what, pyruvate, come here, okay? Let's take the muscle breakdown ammonia, pair it up with pyruvate, you make alanine. That alanine makes its way to the liver, okay? And then in the liver, that alanine dumps the amino group with alpha ketoglutarate to make glutamate, or with oxaloacetate to make aspartate, and then you reform pyruvate, and then that pyruvate can be acted on by pyruvate carboxylase to make oxaloacetate. That oxaloacetate can then be acted on by phosphoenol pyruvate carboxykinase to make phosphoenol pyruvate, and then you work your way up and remake glucose that can then be shipped right back to skeletal muscle, okay? Basically, all I described right now is the alanine cycle, okay? So that's why it makes sense that alanine comes from muscle, okay? Because again, if you think about it, the alanine break down ammonia from muscles, but it also brings carbon, which can be used as feedstock in gluconeogenesis, so that the liver can replenish muscle glucose stores. Okay, so the Urea Cycle, again, it's a cycle that helps us deal with ammonia. Okay, so the thing is that ammonia is usually packaged like in glutamate, for example. Okay, and that glutamate is condensed with carbon dioxide and some other stuff, okay, by an enzyme known as CPS1, which I already talked about before, to make carbamyl phosphate. Okay, and then carbamyl phosphate is converted to citrulline with an enzyme known as ornithine transcarbamylase. Okay, and the thing is, it's literally those two enzymes you need to know from the urea cycle, CPS1 and ornithine transcarbamylase. Okay, and remember that these two enzymes work just in the mitochondria. Okay, and the rate limiting enzyme of the urea cycle is actually CPS1. Okay, and the regulation is actually pretty easy. Okay, you have a substance known as N-acetylglutamate. It's an obligate activator of CPS1, and when it activates CPS1, you have more flux through the urea cycle. Okay, and you may ask yourself, Divine, this is kind of like out of thin air. How does N-acetylglutamate make any sense, right? Well, if you think about it, glutamate is an amino acid. Okay, you get amino acids from protein. Okay, so it should make sense that if you're consuming a ton of protein, right, you're about to build up this nasty ammonia problem for your body. Okay, so a high protein meal should logically, right, increase the production of N-acetylglutamate, which logically should activate CPS1, which logically should help you deal with that incoming ammonia load. Okay, now so the urea cycle, it's a high yield pathway, helps us make urea. But in the urea cycle, one thing I just want to throw in here is that as an offshoot, you make arginine. Okay, and arginine is kind of important. Okay, you can use it to make histones. Remember histones, right? They have positively charged or basic amino acids in them, like lysine or arginine. Okay, and remember that arginine is also used for nitric oxide synthesis. Okay, remember nitric oxide is a vasodilator, and if you're really thinking about this, you may be like, arginine, positively charged, binds DNA, negatively charged, basic amino acids. Again, if you have a CoLA transporter deficit, right, so cystinuria, okay, remember it's a deficit of a basic amino acid transporter, right, so cysteine, arginine, lysine, and arginine. Okay, lysine and arginine are not made. Okay, so you could potentially imagine that, oh, your step 1 exam could word a question that says, oh, this person may potentially have problems with like DNA expression, for example, because they have an arginine deficit, if you may. And if they have that arginine deficit because they're not reabsorbing it from the diet or from the urinary tract, okay, you could imagine that they will have decreased histone synthesis. Although, as far as I know, that having an arginine deficit does not really cause many problems for humans. Okay, and if a person has hepatic encephalopathy, I just put that as an aside. In general, you give lactulose for that, right? So remember, lactulose is converted to lactic acid that can acidify ammonia. Okay, convert it to ammonium. Ammonium is not very reabsorbable, so you basically poop it out. Okay, so that's where I'm going to stop today, and I will pick up from here in a different podcast. I just want to make sure you guys have a solid grounding for metabolism. So we'll just keep going with this and other topics. If you have any questions or you spot any errors, feel free to post a comment or send me an email. Okay, divineinterventionpodcasts@gmail.com. I wish you a wonderful day and God bless. Thank you.